This program was produced by WGBH Boston, which is solely responsible for its content. Major funding for this program is provided by public television stations. Additional support is provided by unrestricted general program grants from the Corporation for Public Broadcasting and the Ford Foundation, and by grants from Exxon Corporation and the National Science Foundation.
On March 22, 1975, a workman in the world's largest nuclear power plant was checking for air leaks by using a candle flame. A fire started. It went out of control, burned for 7 hours, resulted in $150 million in damage and loss to this plant. The chief government investigator of this incident at Brown Ferry, Alabama, concluded it raised embarrassing questions about the safety of reactors throughout the United States. If the Browns Ferry incident had been the worst possible nuclear accident, a recent government study called the Rasmussen Report predicts it could have immediately killed over 3,000 people. 45,000 more would have been severely injured from radiation. 300,000 more would suffer long-term health problems, including cancer and genetic defects. An area the size of the state of Pennsylvania would have been contaminated, and there would have been $15 billion in property damage. But on the other hand, the Rasmussen Report predicts that the odds of any single individual getting killed in a nuclear plant accident in any given year are only 1 in 5 billion. Despite this predicted low risk, nuclear power as a safe energy source has become an emotional public issue that won't go away. Protests like this one at Seabrook, New Hampshire in 1976, ballot measures, lawsuits, grassroots action in American and European cities, the cutting edge of the environmental movement.
From all the dangerous particles of atomic energy to raise...
In this film, Nova examines the growing nuclear safety issue. How the issue is resolved could have consequences affecting everyone on this planet. The 57 nuclear plants now operating in the United States supply 9% of the nation's electricity. About 150 plants operate in other countries around the world. Another 260 are under construction, and as many as 1,000 are planned for completion by the year 2000. If the nuclear industry has its way, they will be supplying half of the world's energy as the 21st century begins. The nuclear safety debate emerged in the early 1970s as a public issue after decades of private scientific dispute. In early 1975, pioneer nuclear physicist Ralph Lapp organized a petition in which eminent scientists declared themselves in favor of nuclear power as a safe energy source.
In my opinion, nuclear power is the very real answer to generating adequate amounts of electricity in the future for a dynamic American economy.
A few months after Lapp's petition, another group of eminent scientists released a counter-statement urging caution and stressing development of alternate energy sources. A leader in this drive was Henry Kendall, MIT physics professor and a founder of the Union of Concerned Scientists.
Almost any source of energy in our society has less inherent risk than nuclear power, in my opinion. Nuclear power, with its enormous accumulations of radioactivity that can cause prompt death, can cause death by cancer, birth defects, and many other kinds of damage, is potentially the most hazardous thing that we can incorporate in our society.
Willard Libby, Nobel chemist, former member of the Atomic Energy Commission, a signer of the Lapp petition.
I think atomic power is an absolute necessity, and we have every reason to believe in its safety. We have a marvelous record. No major industry has ever been started that has a better record than the atomic power industry.
Linus Pauling, another Nobel chemist, a Nobel Peace Prize winner for alerting the world to radiation dangers from nuclear bomb testing. He supported Henry Kendall's declaration.
I believe that nuclear power plants are unsafe, that they damage human beings and are a real hazard.
With scientists lining up on opposing sides, it was almost inevitable that the issue developed into a ballot measure question.
One of the problems is that each nuclear plant is
In
different.
1976, voters in 7 different states struggled with the issue as they tried to decide how to vote.
Are we going to have enough electricity to continue living the style of life that at least I've been living?
The only thing I hear is money and comfort. Does it mean anything safe for our kids, or is it all the time material? I hear material, that's all I hear. This is a housewife talking, baby talk.
I'm really very worried about this genetic problem that can be caused by radioactivity. I don't like the thought of my children having children that are mutants. That really upsets me a great deal.
You're making damn sure that they're not going to have these plants unless they're so safe that you could put all the babies in Oregon in there and they'd...
But the fact is, when you're dealing with nuclear power and radioactive materials, there's a higher standard of care. And there has to be. And, there is a dispute over, how safe should it be? And we're saying it should be safer than it is.
Anthony Roisman, a Washington attorney representing nuclear power opponents.
I don't think that anybody is able to say at this time that nuclear power is safe, but I'm not sure that anybody can say conclusively that it's not safe. I think it's a question which has not yet been resolved. The issue is, what do you do if you don't know the answer?
If the answer can be figured out, it begins with knowing how a nuclear plant works. In the simplest terms, you start with uranium pellets. The pellets are fitted into 30 to 40,000 fuel rods, long, thin tubes made of a special metal alloy, the core, or heat source, of a large modern nuclear reactor. Control rods are interspersed with the fuel rods. All the rods are enclosed in a reactor vessel, in turn enclosed by larger and larger protective structures, often ending with the familiar dome. The fission process, the splitting of uranium atoms, begins when the control rods are separated from the fuel rods. Water surrounding the rods is heated under pressure to 600 degrees by the fission process and turns into steam. The steam circulates under pressure of 1,000 pounds per square inch. 350,000 gallons of water travel through the reactor core every minute. Then, in the form of pressurized steam, it travels through pipes at high speed and turns huge turbine generators that produce electricity. The process is similar to a coal or oil plant, except for the fuel and its special problems. If a large cooling pipe breaks, this would stop the normal flow of water that keeps the fuel rods safely covered. Radioactive 600-degree water would spurt out of the pipe under great pressure as radioactive steam. As the water level dropped, the core would get hotter. A dangerous, uncontrollable melting of the fuel rods would begin, leading to massive release of radiation, resulting in death, disease, contamination, and long-term genetic defects. Plant designers recognized that pipe ruptures could occur. So all modern reactors have emergency systems to maintain the supply of coolant to the reactor core. But this emergency water must reach the core within a few minutes to prevent a melting and the release of radiation. All emergency systems are monitored and can be operated if necessary in the control room. Here, personnel are alerted to the need to use emergency systems by a vast array of lights and gauges. These devices are connected to a large number of cables, which are collected in long trays in a cable spreading room beneath the control room. The thousands of cables, a kind of central nervous system for the plant, are sorted out and routed to the valves, pumps, and instruments that make the emergency systems work. It is extremely complex and crucial to the safety of the plant and to the ultimate safety of the public. Nuclear plants contain enormous amounts of radioactive materials, so extraordinary measures are normally taken inside the plants to protect workers from excessive irradiation. Workers routinely wear protective clothing and masks. They check themselves daily with radiation monitors to make sure they are not contaminated. In some plants, workers are checked periodically from head to toe in a whole body counter. This is to make sure that radiation accumulated in their bodies has not exceeded government-established permitted limits. These are fixed at 2 levels, one for workers, a lower one for the public. But some scientists contend both levels increase the chances of illness, especially cancer. The only really safe radiation level, they believe, is no radiation, inside or outside the plants. Ralph Lapp sees it another way.
People who travel in airplanes get more radiation dose than the whole nuclear industry put together. That's on the basis of high altitude air travel, where because of the fact that you're closer to the space, more radiation comes through from outer space, you get a radiation dose. What I would urge is that the American people understand that radiation is all around you. You live in a sea of it.
This natural background causes about 10%, an estimated 10% of the defective children who are born, the gene mutations producing these defective children, and about 10% of cases of cancer. This doesn't mean that it's all right to add another 1%, as might be done by the high-energy radiation from nuclear power plants if there were a lot of them. This additional 1% means thousands of additional defective children born in the world and thousands of additional cases of cancer. So this argument is a false and misleading one.
Beyond this permitted radiation hazard to workers and the public, there is the larger fear of an accidental and catastrophic radiation release. How close was the Browns Ferry incident to such a catastrophe? March 22nd, 1975, 12:20 p.m., Unit 1 of the plant. Polyurethane, a spongy foam, was being used to fill a 2-inch by 4-inch hole in the wall where cables lead from the cable room to the reactor building. This was done to prevent any potential escape of radiation from the reactor building into the main part of the plant and perhaps out into the surrounding area. To make sure the foam had in fact sealed the hole, a candle was lit, and workers watched the flame to see if it was moved by escaping air. The foam caught on fire. Then the cable insulation. The air draft sucked the fire into the hole, then began to burn cable insulation inside the cable room. After 15 minutes spent trying to snuff the fire out with rags, a decision was made to sound the fire alarm inside the plant. And so the incident at Brown's Ferry was underway. Superintendent Jim Green.
I think there's a lot of misunderstanding on just what the fire was. Now, it was confined to one room, and the room was a concrete room, and it was confined entirely to wiring. But it was not a nuclear accident, and we demonstrated that even under these most adverse conditions, the plant could be shut down safely.
Brown's Ferry accident was a very close call. I've studied it, my colleagues have studied it. We've talked to nuclear engineers at the Brown's Ferry plant who wish to remain anonymous. And they've told us, and we agree, that that accident was in fact a close call.
What exactly happened at Brown's Ferry? The record shows that it was the third fire caused by candle flames and foam. The first two were minor, but no change in air leak testing procedure was made. After this fire began, like in so many accidents, a series of incredible, unpredicted human and mechanical failures had started. Wrong numbers were posted and called to sound the fire alarms. There was insufficient breathing apparatus for firefighters, and the system to refill the air supply was broken. After the fire was over, insurance inspectors said that it was inexcusable that the trays holding the cables were so crowded together that ordinary fire extinguishers would not reach in. As the fire spread, the chemical fire extinguisher in the cable room, which was supposed to trigger automatically, didn't. A metal plate covered the hand switch so it couldn't even be turned on manually. The spray nozzle of a hose would not let the water reach the flames. 20 minutes after the fire started, operators in the control room noticed smoke leaking in, lights randomly blinking on and off, a drop in the power output of the reactor. They noticed that all the emergency cooling system pumps had unexpectedly started. At 12:51, a half hour after the fire began, the problem had become so severe it was decided to scram the reactor, which means reinserting the control rods between the fuel rods to shut the operation down. The heat in the core cannot turn off instantly. It continues to be produced for months after a scram. So cooling water must constantly cover the fuel, even after the control rods are in, to prevent a meltdown and release of radiation. Despite earlier specific warnings by government inspectors, some of the cables for the main emergency system, as well as its backup systems, were all in the same or nearby cable trays. This was in direct violation of federal safety regulations. As the insulation around the cables continued to burn, the emergency cooling systems were shorted out. At 12:55, the entire electrical supply to control and power these systems was lost. By then, crucial monitoring instruments had failed. Engineers could no longer measure temperature or radiation in the core. Athens, Alabama is the nearest town with a fire department, 10 miles away. Chief Artie Bumpus takes up the story.
Really called us a little after 1 o'clock, and when we arrived, there was some wires afire, a lot of wires, several hundred. And of course, they was using their chemicals on it, dry chemical and CO2. We surveyed the situation, and we also tried the chemicals they was using and some of ours, but it failed to put the fire out. And we saw right off that we was going to have to use something else, and of course water being the best extinguishing agent, we recommended that.
With the fire still burning and the emergency systems out of action, the water level dropped from its normal 200 inches down to an alarming 48 inches. After several hours, it was discovered that depressurizing the water would allow a low-pressure pump, not part of the emergency systems, to supply enough water to keep the core covered. This makeshift arrangement is what saved the core from a catastrophic meltdown. Around 7 o'clock, Chief Bumpus's suggestion to use water was finally listened to, and the cable fire was put out in 15 minutes. Why didn't they use water 5 hours earlier?
We could not get permission to use it. We was under their supervision down there, and they wouldn't let us use water.
Problems were not confined to the interior of the plant. The cable fire inside made it impossible to use automatic monitors to check for possible radiation release around the outside of the plant. Air samples were taken in 2 towns close to Brown's Ferry. But in Decatur, directly downwind, the man who was sent to check the radiation monitor had a surprise.
Well, this monitor was not operable at all on the day of the fire.
If radioactive material from Brown's Ferry had been carried downwind to Decatur, instant knowledge was essential to protect the public. Because the first monitor was not working, it was necessary to drive to another. But that air sampler was not designed to give instant information. The filter had to be sent to a laboratory hundreds of miles away for analysis, which took 2 days. And local civil defense officials in charge of evacuation plans did not hear about the fire until 2 days after it was over.
The core was never in danger of melting down throughout the fire event.
The circumstances of that accident would only had to have been casually different. And there could well have been, almost certainly could have been, a catastrophic release of radioactivity. That's no cause for complacency. That's a severe and sharp warning.
Both Superintendent Green's and Kendall's views appear to be justified. Radiation did not leak out of the plant, but it seems to have been a close call. How could a major safety problem develop at a facility like Brown's Ferry? There had been 2 major safety reviews of the plant by the federal government, 207 on-site safety inspections between 1966, when they began construction, and the 1975 fire. Brown's Ferry was presumably licensed to operate under the strictest of federal regulations.
The worst accident we've had in the nuclear program, the fire at Brown's Ferry, was almost entirely the result of regulatory failure to correct problems that had been identified, to reduce the sensitivity of emergency systems to total failure.
I find that the regulation of nuclear power plants is extremely tough, tougher than it was in the past. And I think that the regulation is perhaps going overboard. I think we're getting too much regulation.
They've always regulated them to the possible, not to what is required. And I think that that is probably the single biggest flaw in the theory that the agency is vigorously regulating nuclear power. If it were regulating nuclear power, at least one utility sometime would have found the regulation so onerous that they would have sued them or sought relief. That's never happened. And I think that suggests that the agency has always been careful to be just as tough as the industry could take, but never any tougher. And I don't think that that is sufficiently tough.
The Atomic Energy Act, signed by President Eisenhower in 1954, set up an agency that both promoted and regulated commercial use of the new peaceful atom. Under the Atomic Energy Commission, the AEC, small experimental plants were begun. But private firms resisted getting into the atomic business without insurance protection. And insurance firms were unwilling to provide adequate coverage for this new hazard. Congress urged the AEC to study power plant safety, hoping the findings would encourage insurance firms to provide coverage. The report came out in 1957, but was not generally publicized. It concluded that the outside limits of damage from a nuclear plant accident would result in 3,400 people killed within 15 miles of the plant. 43,000 would suffer severe radiation sickness in an area 44 miles from the plant. 182,000 people in a 200-mile circle would double their chances of getting cancer from radiation exposure. And there would be $7 billion in property damage. With these gloomy figures in mind, AEC Chairman Lewis Strauss led efforts to get the Price-Anderson Act passed. This meant federal tax money provided most of the $560 million in insurance coverage, since private insurance was still reluctant. Commercial utilities then began to move into atomic energy on a larger scale. Larger, presumably safer nuclear plants began operation. So with this experience record and the Price-Anderson Act up for possible renewal, it was expected that a new 1965 AEC safety study would present a more favorable insurance picture. But this time, even with evacuation taken into account, 27,000 deaths were estimated from a major accident. 73,000 would suffer severe radiation sickness. 300,000 would have greater risk of cancer. Property damage would total $17 billion. The Price-Anderson Act was renewed, still at the $560 million level. How enough people could get out of a major metropolitan center in enough time was not clarified. Significantly, the study concluded there was no rational way of working out the chances of such a disaster ever occurring, because there had not been a long enough history of nuclear plant operations on which to base a responsible prediction. They went on to say that it was difficult to prove that nuclear power plants were safe enough to build. At first, the AEC claimed the new ominous figures did not exist. Instead, leaving out the numbers, they reported that a major nuclear plant accident would not be less, and under some circumstances would be substantially more, than the consequences reported in 1957. The actual figures were kept secret for 8 years, until Henry Kendall and the Union of Concerned Scientists used the Freedom of Information Act to open AEC files. They found the safety regulators of the agency had been consistently overruled by the more powerful Reactor Development Branch. As a result, in 1974, the agency was abolished. The Energy Research and Development Administration took over nuclear power promotion. NRC, the Nuclear Regulatory Commission, now licenses plants and regulates safety. Ralph Lapp welcomed the change.
And the Atomic Energy Commission hadn't always behaved in the best way in the public sense. But now we have an open agency. You can get in, I can get in, and do get in, to the Energy Research and Development Administration and the Nuclear Regulatory Commission. And to my mind, the openness of the industry is a real requirement, and I think it's satisfied today.
The secret 1965 study decided it was impossible to determine the odds of an accident occurring in a nuclear plant. Nevertheless, with increased pressure by concerned scientists, the AEC began a new study in 1972. This was led by Norman Rasmussen, MIT professor of nuclear engineering. The $4 million study was released by the new Nuclear Regulatory Commission in October 1975. For the first time, the government tried to estimate both chances and consequences of nuclear plant accidents.
What we did was examine the plant and find out what kind of failures could release significant amounts of radioactivity. As engineers, that's not so hard to do. And then we examined how likely it was to have failures of this type in the plant. Let's presume one of these failures is the rupture of a large pipe. How do we know how likely that is? Well, we examined how often pipes have failed in nuclear power plant accidents, in oil refineries, in fossil fuel plants, in chemical plants. We took the accumulated experience of the last few decades to get an idea of how likely that event was to occur. The same kind of investigation was made to find how likely a valve is to fail, or a motor is to fail to operate, or any one of a number of the components in the plant that might contribute to the release of radioactivity.
The Rasmussen report rekindled the safety debate because it claimed to have examined, identified, and established, with computer analysis, the risk of every possible radiation-releasing accident that could occur in a nuclear plant. Keith Miller of the University of California, computer consultant to the NRC, has his own outspoken private views.
The entire basis of the Rasmussen report is that somehow we trust them to have been able to think of every possible thing which could go wrong in a nuclear reactor and analyze it. Here we've got a relatively new product. We've got 1,000-megawatt reactors, and there's only a few units in operation for only a few years. Nevertheless, they seem to claim to have the analytical ability by testing this component, guessing this probability and that probability, to totally analyze the system, everything that might humanly go wrong with its manufacture, its operation, and end up telling us that here's a new product and it's going to be reliable for 20,000 years. As an applied mathematician, I'm just amazed. I just can't believe it. What you can do with a large-scale computer and a little bit of mathematical analysis.
We as engineers can think of only the failures that we as engineers have come to recognize or imagine can happen in these kinds of systems. There may be a kind of failure that we've never thought of and never seen. However, for that to be true, it would also have to be a very unlikely failure because we've been looking and working with systems of this kind for nearly a century. That is, systems that pump water, pipe it around, turn turbines, valves, and so on. So for there to be a whole new mechanism that we've never thought of or contemplated, it would have to be very unlikely. If it's very unlikely, then it isn't going to contribute very much to the probability of failure of the plant.
In order to prove that a reactor is safe, and this has never been done, one has to identify all the important accidents, each one in this complex structure. Rasmussen claims he's done that. I don't believe it. And we have too many examples in our society of unexpected events. And this is even more true in the complex and intricate structure of a nuclear reactor.
We live in a dangerous world. The Rasmussen study compared the chances of a nuclear plant accident with a variety of natural and man-created accidents. The average chance of any individual dying in a fire in a given year is 1 in 25,000. This tragedy is in Sao Paulo, Brazil. The odds of any person dying from an airplane crash in any given year are 1 in 100,000. Of dying from an auto accident, 1 in 4,000. The odds of someone drowning, perhaps from a flood, like the Teton Dam disaster in Idaho, are 1 in 30,000. The odds diminish when it comes to natural disasters like hurricanes or tornadoes, 1 in 2.5 million. Without taking into account long-term radiation effects, Rasmussen's study contends that the odds are 1 in 5 billion that any individual will die in any given year from a nuclear plant accident, about as remote as you can get. George Kistiakowsky, Harvard chemistry professor, science advisor to President Eisenhower at the time the Atomic Energy Act was passed.
It is very difficult for me to accept the assertions of the Rasmussen report, and I should say that perhaps partly this is because of my long experience with the Atomic Energy Commission bureaucracy. In all my many years dealing with Washington, I would say that that bureaucracy is the most arrogant bureaucracy in the federal government. It's one whose motto seems to be the public be damned. And yet it is not the most intelligent, most competent bureaucracy. And it's the same bureaucracy which prepared, under Rasmussen's management, that report. So why should I believe it?
The critics reject Rasmussen's odds. What do they think are the correct odds of a major nuclear plant disaster?
I believe, and many colleagues agree with this, that if the program continues as it is now, that within the next 10 years, 20 years, perhaps 25 years, that there will be an accident of important size, one that would cause a crippling of the nuclear reactor program in the United States.
Karl Hocevar, who resigned from the nuclear industry in 1974, has a more fundamental reservation about the Rasmussen report.
Rasmussen does not take into account at all the possibility that the safety system itself may be improperly designed. He assumes that it is properly designed and that occasionally a pump or something might fail. Okay? That is one of the reasons why he gets such relatively low probabilities for an accident. We don't know that that safety system will work 99 times out of 100. He's just assuming it will work that many times, and there's test data to prove or to indicate that that may very well not be the case.
For many years, the government has been running tests trying to prove that the emergency systems in already operating nuclear plants will work if a major cooling pipe breaks. These tests are done using computer analysis and scale models of nuclear plants. Until 1976, all tests failed. The heated pressurized water in the scale models did not allow the emergency cooling water to get to the core, and the computers couldn't accurately predict what was going to happen. So if a cooling pipe in a full-sized plant actually does break, no one can yet say with certainty that the emergency systems will really work. Most of the tests are being done at the National Engineering Laboratory in Idaho. In this test, a miniature heating system is being subjected to a blowdown, the term describing what happens when a large cooling pipe breaks.
3, 2, 1, 0. We got a blowdown.
Temperature changes, water flows, pressures, and other measurements from the small-scale system are combined into a computer code. Results from tests on full-scale reactor components are also included. This computer code is then used to predict how a full-scale reactor will behave during a real pipe break accident. It is not entirely theoretical, but it is not exactly the real thing either. Karl Hocevar, who worked on the project, has doubts about it.
We're taking a computer code which has been partially verified with a system that is only 1/2000th as large as the big machine. And we're saying that on the basis of what we know on the small scale, we can predict what's going to happen in the big scale. And physics doesn't work that way.
One partial answer to this problem may be the LOFT reactor, standing for Loss of Fluid Test. Using nuclear fuel, LOFT will be subjected to a real pipe break accident and the emergency core cooling system tested. But LOFT is still a scale model, 1/60th the volume of a full-scale nuclear plant. Are scale model tests of nuclear plants adequate? Manager of the LOFT test program, Dr. Larry Ibarrondo.
Scale models that we are using are indeed somewhat similar also to scale models which are used in other industries. For instance, in the modeling of dams and flood situations where people predict when the river is going to crest and how much land it is going to flood and for how long. The Army Corps of Engineers uses scale models for those type of things. For years we have tested aircraft in wind tunnels, rockets in wind tunnels.
We have here with reactors a situation which is much, much more highly complex, much more difficult to do than aerodynamics. Yet in aerodynamics, only recently have we been able to use computer programs with great success for the design of aircraft. And there, of course, we build aircraft. And there we have constant interconnections between the computer programs, and we can check them out against wind tunnel tests. We build the aircraft, we fly it, we put a pilot on it, a test pilot. We don't go loading the public on this based completely on computer predictions.
Large-scale or full-scale testing of safety systems is not common to engineering. One does not test the San Francisco Golden Gate Bridge full-scale because it's too expensive. Nor does one test the Empire State Building full-scale by starting a fire in the basement and seeing if you can put it out. I mean, you just don't do it that way. What you do is you take the best engineering judgment that you can of the systems, and where it is necessary to scale up a system, you do, but you do it on the basis of reasonable extrapolation or extension of your knowledge. Thus, it is probably never going to be possible to test a nuclear reactor full scale unless there is a true accident.
With full-scale testing out of the question, all that seems to be left is a legacy of test failures using disputed computer codes. These same computer models are the basis for the licensing of nuclear plants by the federal government.
Licensing computer models on which we test whether the present pressurized water reactors have adequate core coolant systems depends upon these same codes which for 5 years have even been unable to predict what happens in these small-scale experiments. Now, when we go to the full size, there's room for a vast margin of error. We may be fooling the American government and public, and what's more disturbing to me, we have indications that we're actually fooling the Nuclear Regulatory Commission and the licensing people within that commission. And there's just not enough leeway with the present system for error in our computerized analysis. If we make too many mistakes in our computerized analysis, this system won't be effective. It won't work.
The Idaho facility primarily deals with pressurized water reactors. General Electric, which designs and manufactures boiling water reactors, the other major type, does its own safety testing in San Jose, California.
Okay, let's go. Hit it.
GE does a variety of safety tests. This one tests the ability of separate parts of nuclear plants to withstand severe earthquakes.
Down. Turn it up real slow. Hertz, sweep back down.
The fundamental behavior of steam injected into cold water is investigated. This test relates to what may happen if the emergency system is called into play. Sections of metal pipe are broken to study the behavior of cracks. Ultrasonic scanners verify that the pipes and welding used in the plants have no flaws. In early 1976, 3 nuclear engineers who worked at the San Jose facility quit because, in spite of the testing programs, they felt nuclear power can never be made safe. One was Richard Hubbard.
I resigned from my management position with General Electric because of my concerns about reactor safety. Design deficiencies that we were finding in the field and in our new, larger scaled-up products, and the regulatory deficiencies and quality deficiencies that I had experienced.
Salomon Levy is General Electric's chief nuclear engineer in San Jose.
I want to assure you that safety comes first in any of our work. Profits or economics clearly are secondary. You know, I could tell you personally that I would quit this corporation if any time I felt that I had to do something for profit when I felt I had to do the opposite for safety.
Hubbard and his colleagues testified before Congress and the California legislature on what they thought had been going wrong.
We pointed out that the GE containment on 19 of the operating plants in the United States, nearly a third of them, could not contain an accident, that over 20 forces had not been considered. Well, in this case, the regulatory process worked because soon thereafter, those plants were ordered to update their containment. We brought up that there were vibrations inside the core of the reactors that weren't understood. Pipes were cracking and instruments were vibrating against fuel channels. Well, GE's response to that was, we're building an $18 million test facility. And I read in our San Jose newspaper last week that they may have it built by 1978. Maybe we'll have some tests by 1980.
I think in reality, the issues they've raised is, I have to say, we're on the way of being solved. I think certainly in certain cases, I think there was some acceleration of the programs because they have focused attention on some of these problems. And clearly, as I've indicated before, we believe we have to be responsive to these criticisms.
As Chief Nuclear Engineer Levy indicates, resignations from the industry have led to acceleration in some safety testing. But that still leaves the public waiting until 1980, when vital tests are scheduled for completion. And what if these tests in San Jose or Idaho show that emergency systems in currently operating nuclear plants are faulty? Should the plants then be refitted to include better systems?
Well, I think that you're limited there by the practicality of engineering a system that's been in operation. And it would seem to me that the real issue is, what is the safety margin that is built into the system, and what is the probability that you would have an accident? That has been, I think, carefully examined by the Rasmussen study, and you see that whole emergency car cooling system is called into play only in the event of emergency. So you must ask yourself, how likely is the emergency? And then back it up by saying, then how probable is it that the emergency system will not work?
If, as Ralph Lapp suggests, existing emergency systems cannot be changed even if tests show they are inadequate, then why bother to do the tests? James Zane of the Idaho Testing Program.
The work we're doing today is trying to get an in-depth understanding or to get precision in our analytical models so we can make a case for perhaps removing some of those conservatisms in the licensing process, perhaps give them a little bit more latitude in the power densities they run at.
In other words, it appears that the computer and scale model Idaho tests are not designed to make plants safer, but to verify the safety of existing plants and possibly relax licensing standards for new plants. Keith Miller sees potential safety problems with this strategy.
It's bad enough that they're telling the American leaders and public that these things are so grossly safe. But perhaps even worse is that there's indications that people within the Nuclear Regulatory Commission, the commissioners themselves, I have a letter from the chairman of the Nuclear Regulatory Commission, these people themselves are believing these grossly optimistic predictions, and that can be extremely dangerous. We can just wipe away certain problems of nuclear safety research, and such as trying to design a more adequate emergency core coolant system, because we say, oh, that's totally improbable. And that can lead to a great relaxation in standards. That can lead to a great inadequacy in our safety systems for our nuclear industry.
How do the critics propose that the problems of possibly inadequate safety systems can be solved? Attorney Anthony Roisman.
I think a good starting point for knowing that plants are safe is to have the Advisory Committee on Reactor Safeguards, which reports to the Nuclear Regulatory Commission, issue a report that says there are no more unresolved safety problems in our judgment. Their last report had about 30, and they have had that number for quite a few years.
Yes, the Nuclear Regulatory Commission has an Advisory Committee on Reactor Safeguards, which lists a number of unresolved technical issues, but that does not mean that they are without solution. What that means is that the experts are requiring additional verification, additional research, to give us an added margin of safety for those issues. I think that the whole question of technical issues of safety has been blown into the open now. It's the sunshine has come in because of these 3 GE engineers who resigned and who essentially cleaned the files out. They purged the system.
In September 1976, Unit 1 of Brown's Ferry, a plant designed by General Electric with safety systems tested in San Jose, went back into operation. The world's largest nuclear plant, supplying 1,000 megawatts of power to the Tennessee Valley in northern Alabama. Superintendent Jim Green.
As a result of the fire, we have certainly had a number of safety reviews and incorporated a number of modifications so that the plant is now safer than it was before.
Since the fire, they have put in sprinkler systems down there to protect these wires, and they've also put in more standpipe fire hose and things. The old saying is to wait till a mule gets out and then close the barn door.
The cables where the fire had started have been realigned so that emergency systems are separated. And the cables are now covered with a fireproof material. GE's chief nuclear engineer agrees that the incident at Browns Ferry led to design changes in other plants.
Subsequent to that plant, I think we have made some design changes in some of these plants, learning from that experience, have assured ourselves that if a fire would take place, it would be terminated quite a bit more rapidly, and have arranged our electrical cables in a way that if a fire occurs in one area, we could still get the signals to all of our instruments by having the cable come from a completely separated area.
Meanwhile, the new policy for checking air leaks at Browns Ferry, according to the Alabama press, is to use feathers. What are the odds of another incident like the one that happened at Browns Ferry? Norman Rasmussen.
Sure, it could happen again. The crudest kind of statistics would say we've now had about 250 to 300 plant years of operation. We've had one such event. So the first rough estimate statistically is that the occurrence of such an event is 1 in 200 per plant per year.
The fact is that worldwide, the nuclear industry has never produced the ultimate catastrophe. However, there have been many nuclear plants where unanticipated problems have occurred. At Windscale, England, there was a fire and partial core meltdown in 1957. Radioactive materials escaped to nearby pasture land. Traces were found hundreds of miles away. Radioactive iodine-131 passed on to humans through contaminated cow's milk can cause leukemia and thyroid cancer. Thousands of gallons of milk were dumped. In 1966, at Unit 1 of the Fermi plant near Detroit, there was another partial core meltdown. The plant is closed permanently. In 1970, the huge Commonwealth Edison plant near Chicago was shut down after 50,000 gallons of radioactive water and steam escaped from the reactor vessel. There were 17 major shutdowns in the first 19 months of operation of the Vermont Yankee plant because of safety violations, fuel rods buckling, and other equipment failures. At Millstone in Connecticut, pipe cracks and leaks of seawater into the cooling system led to a 6-month shutdown in 1972. Turkey Point near Miami, Florida, 5 failures of cooling pumps, leakage of radioactive water. Indian Point near New York City. The government safety inspector quit in 1976, urging the plant be shut down immediately because it's almost an accident waiting to happen. Indian Point is still operating. In another plant, whose name still remains secret, radioactive water was mixed up with water for the plant's drinking fountains. In 1974, reporting on the many nuclear plant incidents, an AEC report said that none threatened public health, but added, the absence of more serious effects is largely the result of good luck. Strict licensing and regulation should provide greater assurance than good luck. But will it ever be possible that the licensing process can guarantee that a Browns Ferry type accident, or worse, won't occur in another nuclear plant? Carl Hocevar.
The licensing process is basically only as good as man is. If we're infallible and we can think of all the possible things that can occur, maybe we can develop a fail-safe licensing process. Since we didn't anticipate what happened in the Browns Ferry, and I suspect we can't anticipate a lot of other things that are going to happen in the future, basing that on past experience, we do not have an infallible licensing process.
Infallible or not, billions of dollars have been invested in hundreds of new plants that are planned or under construction, no matter what the critics say. Do the critics want to close this huge industry down? Keith Miller.
I'm not suggesting that we do away with nuclear power. We have some serious technical difficulties with nuclear power right now, though, and these need to be solved.
If the problems can be resolved, nuclear power can make a useful contribution to the nation's energies. If these safety problems cannot be resolved, then nuclear power is an unacceptable energy source, and ultimately it will simply have to be phased out.
Put it on the back shelf. Use the technologies in other areas, energy conservation and other kinds of energy, that we know are safe, until such time as nuclear power is even proven to be safe or proven to be not safe. And in the meantime, phase out those construction permits and operating licenses that are in existence and halt the issuance of new ones.
The nuclear program in this country has developed for 25 years. There are immense investments in it now. There's professional pride associated with it. And there's been the hope for many years that nuclear power would supply cheap, inexpensive, safe electricity. As someone said, too cheap to meter. This promise is a bit tarnished now. In order to turn this around, one needs citizen action because of the immense size of the industry, its immense political clout. But this can be done. It's being done now in the area of nuclear reactor risks by citizens groups, and it needs the support of the American people.
Citizen groups have indeed organized successful drives to put nuclear plant safety on state ballots. Volunteers and voters at large focused on the growing controversy.
I don't consider myself on any level an expert, but I just understand that I want to take care of the environment. And if I can do it this way by just saying, hey, let's be reasonable, let's just be careful. And I think that's all the proposition is just a plea to be careful.
Not having tested the safety systems and not having any solution for the waste storage, to me, is incredible, because the amount of radioactivity that is being there now is exceedingly toxic, and there are a great number of people in the medical community that are very much worried and very concerned with the consequences of a massive accident.
My children and myself, we are the ones who are going to pay the price if nuclear power is not safe enough. And therefore, I think we need to be very actively involved in the decision.
The nuclear industry, with federal help, fought back. They stressed their safety records and introduced economic fears, as this campaign ad demonstrates.
Another no on Measure 9.
Hello, I'm Kathy Higley. I'm majoring in physical chemistry at Reed College, and I operate our research nuclear reactor. A lot of students, like myself, will soon be out of school and looking for jobs. Our energy supply is very important to us. No energy, no jobs. Please join me and vote no on Measure 9. It would ban further development of nuclear power, a clean and safe energy source. Vote no on 9 and beat the ban.
As nuclear power becomes a public issue, the technical complications are reduced to bumper stickers and 30-second TV spots, as in this advertisement.
The utilities say nuclear power is safe, but ask about radioactive waste leaks and that series of so far small accidents, and they admit there are a few bugs. Still, they say it's worth the danger. But is it? Shouldn't we prove that nuclear emergency systems are safe before we build more plants? Measure 9 simply says yes. But then you're taking the risk. You have to decide.
You have implied that federal
All 1976 ballot measures lost, but the debate is not over. The California legislature did pass 3 laws that achieved the goals of the ballot proponents in that state. President Carter endorsed the Oregon ballot measure in his election campaign. Congress is taking a new look. New state ballot drives are underway, so citizens will continue to be asked to decide these issues. But should this be a voting matter? Or should it simply be left to the experts?
Everyone should decide these important questions. I do think that scientists have a special role to play. They may understand the technical aspects of these problems better than other people. I think that they have the duty of explaining them, not only explaining, presenting the facts, but also expressing their own opinions. That's why I say that I am opposed to nuclear power plants, and I say why I am.
I happen to believe that the citizen has a very real interest in nuclear safety, because after all, he is the person who is at risk. On the other hand, there's a great gap separating the public from the expert. The expert presumably knows what the technology is, what its risks are, but the expert's also a specialist who has a limited frame of reference and sometimes a limited vocabulary. And the public is not apt to understand him very well. Therefore, it seems to me that this is a question of great delicacy for democracy, because sooner or later you have to trust somebody. And if you don't trust government, then who do you trust?
On the one hand, the industry says everything's fine. On the other hand, we hear people in positions of importance saying everything is not fine. And so I'm caught in the middle then. Whom am I supposed to believe?
Leading international scientists disagree. So how can the ordinary citizen ever make a sound voting decision?
Leading international scientists disagree on most everything is certainly true, especially when they're talking about things outside of their field of expertise. And so one has to judge how well a man has studied and understood the issue he's talking about. Does he fully know the details of it? Because scientists are no better than anybody else at making a decision in a technical area unless it's one that they've studied.
Citizens are able to understand these issues. They are able to resolve the conflicting claims. And the whole history of the nuclear program, with its difficulties, its poor reliability, its poor accident record, speaks for itself, and is one of the reasons why the nuclear program is in so much trouble presently.
Pressure by citizen groups, scientists, and the growing number of people who quit the industry and the government agencies all have helped focus attention on the whole question of whether or not nuclear power has yet been proven to be a safe energy source. For any improvements or changes, it seems likely the same kind of pressure will have to intensify. Those opposed to our growing dependence on nuclear power will have to press for major commitments to energy conservation, an intensive development of alternate energy sources. Those in favor will have to hope that the ultimate accident will never happen. Meanwhile, nuclear power plant risks continue. How high or low, we probably will never really know. Should we continue to live with a technology with such potential hazards? A technology that, like the incident at Brown Ferry, can be disrupted by a candle flame?
This program was produced by WGBH Boston, which is solely responsible for its content. Major funding for this program was provided by public television stations. Additional support was provided by unrestricted general program grants from the Corporation for Public Broadcasting and the Ford Foundation, and by grants from Exxon Corporation and the National Science Foundation.